A coffee appliance PCBA can look inexpensive on paper while leaving the most consequential engineering work unresolved. Two quotes may list the same laminate family, layer count, nominal thickness, copper weight, surface finish, board size, and quantity, yet describe very different obligations once the board must heat water, switch a pump, interpret temperature, and report faults within the finished machine. Visible specifications provide a useful starting baseline. FR4 construction, 2 layers, 6 mm thickness, 1 ounce copper, and HASL finish can align early discussion around material, mechanical format, copper reference, and finish. They do not establish input conditions, trace geometry, relay selection, heater load, sensor behavior, firmware responsibility, operating temperature, inspection requirements, or acceptance criteria. A public board description is not project approval. The critical question is not simply which supplier offers the lowest unit price. It is whether each commercial offer includes the same scope, carries the same risk, and assigns the same decisions to the same party. A lower quote may exclude a fixture, assume an alternative component, omit firmware handling, limit inspection, or treat a pilot build as a routine assembly order. The price is tidy. The comparison is not. Start by aligning the design baseline. Confirm the exact Gerber revision, assembly drawing, BOM revision, board outline, connector requirements, stack-up, and assembly scope. Require each supplier to state exclusions in writing. Before any award decision, establish the electrical and thermal context as well. Input conditions, heater and pump loads, relay logic, sensor use, thermal limits, and expected fault behavior. This matters because 1 ounce copper alone does not establish safe current handling. Trace width, copper distribution, thermal rise, duty cycle, enclosure conditions, connectors, and the overall appliance architecture all affect electrical and thermal performance. In the same way, a HASL finish identifies a finish discussion, but does not itself prove a restricted substance status for every material and component in the completed assembly. Component sourcing needs the same discipline. The quote should disclose whether pricing assumes customer-supplied parts, distributor-sourced parts, brokered supply, or substitution subject to approval. It should define what happens when a component becomes unavailable. Does the supplier issue a new quote, initiate a design review, or wait for buyer approval? Alternative components should not quietly enter the build without a documented technical review, especially where they may affect control behavior, serviceability, or future supply. Testing must also be separated from appliance validation. AOI, solder joint inspection, and assembly checks can identify process-level issues. They do not prove that the final coffee machine heats, pumps, times, and faults correctly in its enclosure. Functional testing should identify the fixture responsibility, firmware revision, stimulus conditions, pass or fail criteria, record format, and process for ambiguous results or failures. The evidence must follow the build. A useful test record is tied to the board revision, firmware version, component configuration, and build lot. That connection supports problem solving during pilot production and helps distinguish a design issue from a component, assembly, or change control issue. It also sets appropriate limits on the result. Passing a defined functional sequence does not automatically establish lifetime performance across every water condition, voltage variation, ambient temperature, or consumer use pattern. Lead time requires equal care. One supplier may count from complete file release. Another may begin after components are available, engineering review is approved, a fixture is ready, or payment is confirmed. Record the starting condition beside every quoted date. An early estimate should not be converted into a delivery commitment without that basis. For a coffee machine control board, narrow questions create the strongest comparison. What voltage and current does the heater path require? Is the relay switching the load directly or controlling a downstream driver? Which NTC curve, tolerance, and placement apply? What should happen when the sensor is open, shorted, slow to respond, or exposed to an unexpected thermal gradient? How is pump timing tied to temperature logic, and which firmware revision is being evaluated? A documented RFQ turns those questions into comparable evidence. It identifies what is included, what remains open, and which decisions can change cost or timing. Only then does a unit price represent a meaningful commercial choice rather than an incomplete engineering assumption.